Hello everyone. So in this video, we will talk about the R-square and the analysis of variance or ANOVA for the simple linear vectors. So so this is the output for the previous exam for the ALES and GPA exam, right? So we talk about this table, and today, and in this video, we will talk about this table and this table, right? So one thing is, so this is the Excel output, okay, this part. You will have the same thing from the R output, okay, so, well, this thing is, so you see this table below, let's say this is table 1, this is table 2, let's say this is table 3, okay. So this one is a little bit related to table 3, okay, this part, the estimate, the standard error, and so on and so forth. This is what we get from R. And the residual error 3.23, just look at it, 3.23. So this is adjusted R square 0.901, the adjusted R square. And there's a little bit twist here. This is R squared, right? This is the multiples R squared here, and the R squared here are the same. So this part is T1. Okay, the thing is T1, right? Table 1. In fact, this part, right? This part, and let me just. Okay, this part, this green part is a little bit about on this thing, which is T2, okay? So this is T1, T2, and T3, and we also have another table, another result in R. You will see the cause in the recitation part, and this is completely T2, okay? This is completely T2. So I know that you don't have anything to say about this, but now please note that this is R and this is Excel, okay? You can have both of them from both softwares. And we will now see what is table. We have already seen table 3, right? Now we will talk about first table 1, and then we'll talk about table 2. Okay. So in the Excel output, we have something called R squared, okay, which is called the coefficient of determination. The coefficient of the determination. So what is it used for? Well, it's the proportion of the variability in the y values explained by the model that we fit. Okay, so the R squared is the proportion of the variability which can be explained by the model that we fit. Okay, so it's the variability that we can explain by the model that we have already, let's say, regressed, right? By the regression model. So what we can say is that, well, if this explanation, if the ratio of this explanation is high, then it's good, okay? If the explanation is low, then there's a problem with your model. So in order to understand this, we will just first define some new let's say, new definitions, let's say. So the first thing is what we call an SST, okay? Which is in fact SYY. And this is what? This is YI minus Y bar. So this is what we call the total sum of squares, or sum of square total, SST. And this is the total variability in the Y values. What is the total variability? Again, please consider the S square where you don't have any regression or anything like that. S square was equal to, you just sum, we just use x's, but here I can use yi, just change the variable name. That's equal to yi minus y bar squared divided by n minus 1. Remember that this the estimator for the sigma square. So what we did was we just calculate the sum of the deviations around the mean. Okay? So what we do is this is the first variable, this is the value of the first observation minus the average. So this is the distance between the average, right, and the variable. We just square it and sum them. Okay. So this is the total variation in the data, okay? Total variation in the data, right? So what we do is we just then divide it by the almost n, and we just find the variation per unit, okay? The variation per unit. And this is what we call, in fact, the variation in the square root of s squared, which is equal to s. That's the standard deviation. What is this? This is the deviation around the mean. And just take a step back. What we say about random variables is that there are three important measures. Okay, the first measure is where is the center, and the second measure is, well, what is the deviation around the center? And this s square, okay, this s just calculates the estimator. It was an estimator for sigma, so it just calculates the estimator for the deviation around them. And how we find it? This is the formula, right? This is the formula. We say that um, we just sum all of the deviations around the mean and divide it by to the number of observations. So just look at here. This is the just look at here. Um, this is the total deviation from 1 to n. Yi minus y bar. So this is the deviation from the average. Okay, so this is the total deviation from the average. Okay, so what we know is that, well, you can just write, this is only, of course, available for the linear regression case, okay, because just look at it, this is, you will understand what I mean. So what you can do is that this total variability, SST, which is the yi minus y bar, can be divided into two parts, SSC plus SSR, right? And what is SSC? We know what SSC is, right? Yi minus, oh, sorry, this is the SSC, right? So this is just vice versa. Let me just please change this. Okay, so the total sum of squares, which is yi minus y bar, can be broken into two components. The first one is the SSR, and the second one is the SSC. So what is SSC? We know this. It's the observed value minus the predicted value, okay, plus SSR. This is what we call a regression sum of squares, and it's given by the yi hat, the estimated value minus the y bar. So, for example, let me just try to give you an intuition about what we mean. So assume this is the regression line. So assume we have some data like this, right? And assume we have, this is my y bar. This is my y bar, okay? And again, so this is my y hat equal to b0 plus b1x, right? So let's think about this point. Okay, let's think about this point, right? And let me try to write it with blue. Okay. So this is what? This is, for example, this is yi, right? Sorry, this is what? This is yi, right? And so, of course, this is what? This is xi, right? And the value that it just corresponds to here is, this is x, sorry, not x, but this is yi. Okay. So this is yi. Okay. So this point is in fact xi, y, but I'm just putting yi. So what is this point here? This point here. This point here is it's simply yi hat, right? Let me just, okay, let me just make it with orange so that doesn't get, okay. So this is what you call a yi hat. So this is yi, this is yi hat, and this is, of course, the green one is the y bar, right? And this is y bar. So what we look at is that, well, we just distribute the distance between what we observe, okay? And let me just take another color. This is what we observe here, yi. The distance between these two, okay, yi minus yi hat. Sorry, this distance between yi and yi hat, and this one is the distance between yi and y bar. So what we do is that we just distribute the distance yi minus y bar. Okay. Remember, what is this? This is the ordinary measure that we are interested in at the very beginning of our lecture. We say that the deviation around the mean is very important for us. Okay, so this is the deviation around the mean. We just distribute this into two parts. The first part is, well, the distance up to here, okay, up to here. What is this? This is yi hat, the prediction or the point on the line minus y bar, right? yi hat minus y bar, just look at here, yi hat minus y bar, right? And plus what? Plus the difference between yi, which is here, yi minus yi hat, yi minus yi hat. Okay? So if you just sum them up, you will see that, well, these two just cancel. These two would just cancel, right? So the distance between the average and the observed value is equal to the distance between your prediction and the center line, okay, the average, plus your observed value and your estimated value. Okay, so what you're trying to do is, well, you say that, well, this is the overall average without making any model, and this is the new average that is found by making a model, okay? So this is the average that you obtain from the model, and this is the average that without making any model. So you just divide the difference between the grand average and your observed value into two parts. And it turns out that, of course, it's not always the case. This is only true for regression. If you just take the square roots of them, okay, and if you just sum them up, right, sum them up, which is this part, well, this summation still remains valid. What does it mean? So you can still have this equality there, but it's not the case. So for example, you cannot write a minus b is equal to what? C minus b, okay, plus what? yi, a minus c. So if you just sum them up, this c cancel, okay, this c is just cancelled, you have a minus b. But if you just take the square root of this, okay, if you just take the square of this, sorry, if you just take the square of this, well, it's not anymore equal to each other, okay, that's not true. But this is true for what? This is true for this regression. So what I do is I just broke the total variability into two parts. The variability, okay, that is caused uh, by the error, which is SSC. So that's the difference between the model average and your observed value. And this is SSR. This is the difference between the model average and the grand average. Okay. So in a good model, if you have a good model, if you have a perfect model, what you will observe is that your model is so good so that, well, there is a very perfect relationship between y and x so that yi is almost equal to yi hat, okay? So if you have a good model, if you have, okay, a good model, right? So if you have a good model, okay, then you have your read value will be almost equal to your observed predicted value. Okay, so what does it mean? You can predict the observations very, very well. If you can predict the observations very, very well, what does it mean? It means that, well, your SSC will be almost equal to 0, right? If SSC is equal to 0, because SSC is yi, your real value minus the predicted value. If SSC is equal to 0, what does this mean? It means that SST, your total variability, is equal to SSR. Okay, this is almost equal to SSR, right? So what does this mean? It means that, well, you can predict. So this is the total variability without a model. Well, you can, and this is the regression sum of squares, which is the variability due to your model, right? This is the difference between your model's prediction and the grand average, or your model's average and the grand average. So this is the variability caused by the model. The variability caused by the model is almost equal to the variability in the natural variability. So what does it mean? You are able to explain the total variability with your regression model. Okay, and what is R square? R square is simply 1 minus SSC divided by SS total, or if you just plug in the values, that's equal to SSR divided by SS total. Okay. So if your model is very good, then SSR is almost equal to SST, which means your R square is almost equal to 1. Okay, okay. So in fact here, these are the written part of what we have talked so far. And R squared is equal to SSR divided by SST, or 1 minus SSC over SST. And R squared is between 0 and 1. Why? Because if SSC is 0, then R squared is equal to 0, which means you have a perfect fit. If you have a very, very poor fit, okay, if you have a very poor fit, what does it mean? Your SSR is equal to 0, then you have R squared is equal to 0, right? Okay. So this is what we have in terms of a good fit. R squared is almost equal to 1. Okay, remember, this is R squared was SS R divided by SS total. So this is almost equal to 1. What does it mean? You are, so this is the total variability. If this is the variability explained by the model, so the variability explained by the model is almost equal to SST. Okay? And this is a poor fit where R squared is equal to 0. What does it mean? Well, you cannot explain any variability by your model. You see, so this is your regression line, but regression, well, there is not a good relationship between X and Y, right? Hence, it means that, well, you cannot explain the variability using X. What does it mean? The model that you just predicted, you just built, which says there's a relationship between Y and X is not a good model, is not a good thing. And one more thing about this is that if, okay, so if this is a very bad model, if this is a poor model, then SSR is almost equal to 0. And what was SSR? SSR was, remember, it was yi hat the prediction minus the y bar. So if SSR is equal to 0, it means that your predicted value is almost equal to y bar. Okay, so SSR equal to 0 means your prediction is almost equal to y bar. So what does it mean? This is your predicted value, which is b0 plus b1x. If this is equal to y bar, what does this mean? This means that, well, there is no association, right? No association with what? With x bar, right? It means that, well, instead of finding a model which depends on x, you can just take the average of y's, and this is your prediction. Okay, so it says that instead of prediction, just use the average, just use the y value, because your y variable does not change with x. In fact, you can see it in this plot as well. Okay, so in this plot, you have the prediction line, you have the linear regression line, which is like this. And it turns out that, well, this prediction line, this regression line is very close to what? Is very close to y. Okay? So For example, in our Alice example, the R square is very high, 91.3%. What does this mean? The total variability in the data, so in another words, we can explain 91, almost 91% of the variability in the data, right, by using our regression model. Okay? So, okay, 91 is good, but well, how large of R square is considered to be a good fit or to be a very good fit? It very much depends on the context that you're just working. So, for example, if you're just working in a chemist who just makes experiments in a high precision in a laboratory with high precision equipment, then R square should be very, very close to one. Okay, but if you're a social scientist, okay, who are just analyzing a human behavior, then R square of 0.60 could be a very, very good fit because you're just working with people, and it's very hard to estimate the behavior of the human by just using let's say predictor variables. Okay, so R square just depends on the context that you work on.